Chapter 6, the first section is on discrete probability distributions. And then the second section is on a specific type of discrete probability distribution called a binomial probability distribution. So the first thing that we really need to do is talk about some definition. So some preliminaries first of all. A random variable is a numerical measure of the outcome of a probability experiment so that its value is determined by chance. Random variables are typically denoted using capital letters such as capital X. So a random variable, we talked about variables way back in chapter 1. So a variable is a variable. It's an item of interest that we could measure or quantify or distinguish a value for an individual that we are studying. So a random variable just means that the specific value that we're going to be able to record is going to be random. And specifically, we're talking about a numerical measure. Before, we talked about things like if you put your hand in a bag of M&Ms and draw out an M&M, what's the probability it's yellow? Well, that's not exactly a random variable because yellow is not numeric. But if I said I put my hand in a bag of M&Ms and I draw out 3 M&Ms and I want to know how many of the 3 M&Ms are yellow. Well, if I draw out 3 M&Ms, then the number of yellow M&Ms could possibly be 0, it could possibly be 1, it could possibly be 2, it could possibly be all 3. So looking at it from how many of the M&Ms are yellow, I'm now getting a numeric result, and it's a random result because when I stick my hand in and randomly pull out 3 M&Ms, the specific number that are yellow is going to be determined by chance. So that's what we're talking about with a random variable. It's got to have a numeric measure. So it has to be quantitative, it can't be qualitative, and it has to be determined by chance. Now, a discrete random variable has either a finite or a countable number of values. We've talked about discrete variables versus continuous variables before. So really the distinction is the same. The difference is we're talking about random variables now rather than just variables in general. So again, a discrete random variable has either a finite or a countable number of values. The values of a discrete random variable can be plotted on a number line with spaces between each point. A continuous random variable has infinitely many values. The values of a continuous random variable can be plotted on a line in an uninterrupted fashion. So basically, discrete is countable, continuous is not countable. That's how we distinguish between the two. Now, this bit with the space between the points on the number line and so on, again, if I'm talking about reaching my hand into a bag of M&Ms and pulling out, let's say it's 4 M&Ms instead of 3 M&Ms, and I want to know how many are yellow, then the possible outcomes are that 0 could be yellow, 1 could be yellow, 2 could be yellow, 3 could be yellow, all 4 could be yellow. So the only outcomes are literally 0, 1, 2, 3, or 4 if I'm talking about how many yellow M&Ms I get out of 4. So I couldn't have like a half or 2.3 or anything like that. Now, on the other hand, a continuous random variable, if my values are possibly from 0 to 4, but if it could be anything in between 0 and 4, then that would be continuous. So there again, I would be talking about measuring something. So maybe I would be randomly selecting a brick and I want to know how much does that brick weigh? Well, probably it couldn't weigh 0, but say it could be anything between 0 and 4. It could literally be fractions and decimals and stuff in between 0 and 4. So we've done this kind of problem back in chapter 1. Again, the distinction here is that we're talking about a random variable instead of just a variable, but we tell it the same way. So determine whether the random variable is discrete or continuous. So A, the number of defects in a roll of carpet. So if I randomly select a roll of carpet, that makes it a random variable, and I'm going to determine the number of defects in that carpet. How would I determine the number of defects? I would count the number of defects. So that would make this a discrete random variable. B, the distance a baseball travels in the air after being hit. So a baseball gets hit, it travels a certain distance, and then it hits the ground. So our random variable is how far it travels before it hits the ground. How would we determine the distance that the baseball travels? Would we count it? We would not count it. We would have to measure it, like with a measuring tape or a radar or something like that, to be able to determine that distance. So that makes this continuous. So that would be a continuous random variable. C, the number of points scored during a basketball game. Again, if I randomly select a basketball game, the number of points that's scored is a random variable. How do I determine the number of points scored? Well, we count the number of points that are scored. So this would be discrete. The square footage of a house, if I randomly select a house and determine the square footage, that is a random variable because I'm randomly selecting the house. How do you determine the square footage? Do you count it? You do not count it. You have to measure the square footage in some other way. So that makes this continuous. Most likely you would figure that square footage by measuring like the length and the width and calculating it. Now, I said we're going to be studying probability distributions. For the rest of chapter 6, we are specifically going to be looking at discrete probability distributions. So outcomes are going to be countable. When we get into chapter 7, we'll start looking at examples of continuous probability distributions as well. But for now, we're going to be dealing with discrete probability distribution. So the probability distribution of a discrete random variable x provides the possible values of the random variable and the corresponding probabilities. A probability distribution can be in the form of a table, a graph, or a mathematical formula. So for this section, we're going to be looking at tables and graphs. When we get into the next section, we'll also throw in mathematical formulas that we can use as well for determining a probability distribution. So back in chapter 5, we talked about probability models. So a probability model listed the outcomes along with the probability of the outcomes. A discrete probability distribution is the same thing, except for a discrete probability distribution, the outcomes have to be numeric. So like we talked about probability models in chapter 5, we looked at like M&Ms, right? So the possible colors are yellow, brown, orange, blue, red, and green. So we listed those colors along with the probabilities, and that made up a probability model. Well, that can't be a probability distribution because the outcomes are colors, not numeric. But a probability distribution is just like that, except the outcomes are numeric. So in fact, we have the same rules. If P of X denotes the probability that a random variable X equals X, then if we add up all the probabilities, it has to add up to be 1. And each of the probabilities has to be something between 0 and 1 inclusive. So all of the probabilities individually have to be something between 0 and 1. And if you add them all up, it has to add up to 1. So we had problems just like this in chapter 5, except we were talking about probability models instead of probability distributions. So determine whether each distribution is a discrete probability distribution. If not, say why. So we have the numeric outcomes 0, 1, 2, 3, and 4. And then we have the probabilities, 0.2, 0.2, 0.2, 0.2, 0.2. So our question is, could this be a probability distribution? Yes, if you take a look at the 0.2, 0.2, 0.2, 0.2, all of those are between 0 and 1. And if you add them all up, it adds up to 1. So the sum of the P of X equals 1. So the answer is yes, this can be a probability distribution. How about this one? So if we add all those probabilities up, again, it adds up to 1. Each of these probabilities are between 0 and 1. So yes, this can be a probability distribution. Can this be a probability distribution? That is negative right there, right? So this right here, this probability, so to speak, is not between 0 and 1. So because of that, this is not a probability distribution. Even if it adds up to 1, the fact that that's negative makes this not a probability distribution. How about this one? So again, if we add up all of the probabilities here, first of all, they're all between 0 and 1. It's kind of boring because these are all zeros and we get 1 here, but it does add up to 1. So yes, this could be a probability distribution. So this would be a case like where we always get 5. It's impossible to get 1, 2, 3, or 4. We always get 5. What about this one? So if you add up these, this adds up to 0.95, not 1. So this cannot be a probability distribution. So again, it's the same basic idea as when we've talked about probability models. It's not really that different, other than a probability model can have non-numeric outcomes. A probability distribution has to have numeric outcomes. So take a look at this example. We're going to see this example throughout. I just took this straight from the book. Suppose a particular basketball player is going to shoot 3 free throws. Let the random variable x represent the number of shots made. Then x equals 0, 1, 2, or 3. The table to the right shows a probability distribution for the random variable x. Graph the distribution. So for this particular basketball player, this is their probability distribution when it comes to how many are they going to make if they shoot 3 free throws. So if they shoot 3 free throws, they could make 0, they could make 1, they could make 2, they could make all 3. Those would be all of the possible outcomes if the person shoots 3 free throws. So again, this is one possibility depending on the particular basketball player. So this particular basketball player seems to be a relatively decent free throw shooter. There's hardly any chance that they're not going to make any. It's a low chance that they're going to only make 1. It's a much higher chance that they're going to make 2 or all 3. And we could verify that it's a probability distribution. All of those are between 0 and 1. And if I add up 0.01 plus 0.10 plus 0.38 plus 0.51, that does add up to 1. So this is a probability distribution. So I'm asking you to graph this distribution. And I have provided a grid that we can do this on. So basically what we make is similar to a bar graph. The height of the bar, so to speak, is going to represent the probability. Since it's discrete, though, we can only have the outcomes literally of 0, 1, 2, or 3, right? The player can't make 2.5 shots if they shoot 3 times. They're either going to make 0, 1, 2, or all 3. So the way I'm going to do this is this. I'm just going to use a line. So the probability of making 0 shots is 0.01. Now 0.01 would be right really just barely above 0 right there. So I'm just going to put a point right there, right above 0. And that's representing the probability of making 0 of the shots. The probability of making 1 is 0.10. That's right here. So I put that point right above the 1, and I'm just going to connect that with just a line so that that's representing the probability of making 1 shot. The probability of making 2 shots is 0.38. So that's going to be maybe just around there, just below the 0.4 line. So I'm going to put a point there, and I'm going to connect that. And the probability of making all 3 is 0.51. And so that's just barely above the 0.5 line right there. And so I put a point there and I connect it with this line. So this graph is representing this probability distribution. So back here, we said that a probability distribution can be in the form of a table. So there's the table form, or in the form of a graph. So now we've created a graph form, or it could be in the form of a formula. And we will see that a little bit later on when we get into binomials. So we understand what a discrete probability distribution is. One thing that we do with probability distributions, just like we do with data, is we like to be able to describe probability distributions. So we'd like to be able to find like mean and standard deviation. So that's what we're going to define next. The mean of a discrete random variable is given by the formula mu sub x. That subscripted x there is the random variable. So if our variable is x, we're going to find mu sub x. And that's going to equal to the sum of brackets. And inside the brackets, we have x times p of x, where x is the value of a random variable and p of x is the probability of observing the value x. So x is going to be representing like the 0, 1, 2, 3. P of x is representing the corresponding probabilities, 0.01, 0.10, 0.38, 0.51. So if I want to compute the mean of the discrete random variable shots made from the previous example, then I can do that by using this formula. So again, if I want to find the mean for this probability distribution, then I've got my x, I've got my p of x. So I'm going to multiply the outcome times the probability, and when I add that up, that'll give me the mean. So in other words, I'm going to take 0 times 0.01, and that'll be 0. I'm going to take 1, the outcome, times 0.10, the probability, and that equals 0.10. I'm going to take 2, the outcome, times 0.38, the probability, and that'll be 0.76. I'm going to take 3, the outcome, times the 0.51, the probability, and if I do that, that'll be 1.53. So I've taken each outcome times its probability. I get this. And so the mean of our random variable x, the number of shots made, is going to equal 0 plus 0.10 plus 0.76 plus 0.53, or 1.53, I should say. That is 2.39. That is the mean for our random variable shot made in this particular case. So what does this mean? This means that if I repeat the experiment a large number of times, now what's the experiment? The basketball player shoots 3 shots. I count how many they make. Then they shoot 3 more shots. I count how many they make. They shoot 3 more shots. I count how many they make. And so on and so on and so on. So maybe on the first set of 3 shots, they make 2. On the second set of 3 shots, they make all 3. On the third set, they make 2 again. On the fourth set, they only make 1. And so on and so on and so on. They keep shooting 3 shots, and I count how many they make. They shoot 3 more, I count how many they make. 3 more, I count how many they make. If we do that a large number of times, and if I calculate the average of how many they make, they're going to make about 2.39 shots per experiment on average. So on average, each time they shoot the set of 3 shots, they're going to make 2.39 of the 3 shots. Now, can they really make 2.39 shots out of 3? No, they can't really do that, but that is what happens on average. So that's what this is saying right here, the interpretation of the mean. Suppose an experiment is repeated n independent times and the value of the random variable x is recorded. As the number of repetitions of the experiment increases, the mean value of the n trials will approach mu sub x, the mean of the random variable x. In other words, let x sub 1 be the value of the random variable x after the first experiment. Let x sub 2 be the value of the random variable x after the second experiment, and so on. Then x bar equals x sub 1 plus x sub 2 and so on plus x sub n divided by n is going to approach the true mean. The difference between x bar and mu sub x gets closer to 0 as n increases. In other words, what's happening in the sample is going to approach the theoretical mean as we repeat the experiment. So that's another way of thinking about the law of large numbers. So the figures below illustrate the mean of a discrete random variable. Both show simulations of the mean number of free throws made versus the number of repetitions of the experiment. So like if this is my free throw experiment, so what I'm doing is keeping track of the average that's been made. On their first experiment, maybe they made all 3. Then the next experiment, they made fewer. And so we found the average and so on. So this is a running average of how many they're making out of the 3 shots, like I was explaining. As the number of repetitions go up, so here we have 100 repetitions of 3 shots, and the average that's happening in the sample is approaching the theoretical probability. Now they wrote 2.4 here, but it was really 2.39. And then here's just a second simulation of the same thing. So it started off different, but again, as we repeat the experiment more and more times, it approaches the true mean. So this mean value is often referred to as the expected value. It's what we expect will happen in the long run. In the short term, we may not have the mean, but in the long run, that's what's going to occur. It's because of this kind of thing. I've used this example before. This is how casinos and insurance companies and so on are guaranteed profit. They know what's going to happen in the long run based on probability. They know what's going to happen in the long run. So they set up their games or they set up their rates based on what's going to happen in the long run, ensuring them in the long run the profit. So the mean of a random variable is often called the expected value, E of x, of a random variable because it represents what is expected to happen in the long run after a large number of trials.